Hi, my name is Andrew Roberts. I'm a design engineer in the Signal Conditioning Group at Linear Technology. Today I'm going to talk about the LTC 2063 Micropower Zero Drift Operational Amplifier. The unique combination of low power consumption, low offset voltage, and low input bias current over temperature makes the LTC 2063 an excellent choice for many applications. I will now highlight some common errors in amplifier circuits and show how the LTC 2063 minimizes them. Input offset voltage is an error which appears at the input of the operational amplifier and varies with temperature. When used in a closed-loop configuration, this input offset voltage is multiplied by the noise gain and appears at the output of the circuit. For high-gain circuits, this can become a large source of error. For example, in a gain of 1000, a 1 millivolt input offset will lead to a 1 volt error at the output. Zero drift amplifiers like the LTC 2063 self-calibrate to null the input offset voltage, resulting in an extremely low temperature-stable input offset voltage. The LTC 2063 has a maximum input offset voltage of only 5 microvolts and a maximum drift of only 50 nanovolts per degree Celsius over the entire minus 40 to 125 degrees Celsius temperature range. Input bias current conducts in source and feedback components, creating unwanted errors in operational amplifier circuits. These errors are most problematic in circuits with high impedances. In a transimpedance amplifier circuit, for example, large value feedback resistors are often used to convert small currents at the input to large voltages at the output. In these circuits, the input bias current will react with the feedback resistor and cause an error at the output. For example, 1 nanoamp of input bias current reacting with a 100 mega ohm feedback resistor will generate 100 millivolts at the output. The LTC 2063 has been designed to minimize input bias current. The maximum input bias current is 20 picoamps and does not exceed 100 picoamps over the entire minus 40 to 125 degrees Celsius range. This allows precision measurement in high impedance circuits. The LTC 2063 has been designed with a focus on minimizing power, typically consuming only 1.4 microamps of supply current. The LTC 2063 also offers a shutdown pin, which further reduces power consumption to 90 nanoamps typically. This can help to alleviate power consumption concerns in battery-powered applications and applications where the amplifier circuitry is expected to be idle for long periods of time. In this example, a portable oxygen sensor circuit is enabled to take a reading only occasionally. The oxygen sensor generates a current that results in roughly 10 millivolts at the input when in air. The input voltage is amplified by a factor of 100 to yield an output of approximately 1 volt. In this example, the amplifier is left in shutdown for a majority of the time and enabled approximately every 100 milliseconds. Each time the amplifier is enabled, the output responds, allowing a measurement to be taken. The amplifier is then disabled once again to conserve power. The oxygen sensor at the input is left undisturbed and kept at its final settled value to prevent long turn-on response times from the sensor. Plotted at the top is the total charge consumed by this circuit, which is the integral of the supply current with respect to time. The low offset voltage and input bias current of the LTC 2063 result in excellent accuracy, while the shutdown capability allows power consumption to be minimized in this application. Many amplifier circuits run into problems due to an amplifier's limited input and output ranges. The LTC 2063 features a rail-to-rail input stage allowing input signals to exceed the supply rails by up to 100 millivolts. The LTC 2063 also features a rail-to-rail output stage, allowing the output to swing within millivolts of either supply voltage. In high-side current sense applications, the input pins are connected across a shunt resistor to sense the current drawn from the supply. A scaled replica of this current is transferred to the output resistor, yielding a ground reference voltage output. In these applications, the amplifier inputs must operate at the positive rail. The LTC 2063's wide input range allows operation without additional supplies. The LTC 2063's low input offset voltage allows this circuit to achieve 86 dB of dynamic range with only 100 millivolts of maximum shunt voltage. Low-side current sense applications also benefit from the wide input common mode range of the LTC2063. In this example, a shunt resistor is used to sense the supply current, and gain is applied to scale the output signal. The amplifier must maintain precision while its inputs operate at the negative rail. The LTC2063's rail-to-rail output also allows the output to swing close to ground to measure small currents. Electromagnetic interference, or EMI, can cause significant errors when operational amplifiers are applied. High-frequency electromagnetic signals tend to become rectified by an amplifier's input stage, causing a DC shift in offset voltage. EMI rejection ratio is used to specify how well an amplifier rejects this rectification. The LTC2063 features an integrated EMI filter on the input pins, which attenuates high-frequency signals before they have an opportunity to be rectified. In addition to significantly improving EMI performance, this simplifies design, reduces component count, and preserves accuracy. The LTC2063 packs all this performance into extremely small SC70 and TSOT packages, while operating over the -40 to 125 degrees Celsius temperature range. The SC70 has a footprint of only 4 square millimeters, providing significant space savings compared to a more common MS8 package, which is shown here only for comparison. Thank you for watching, and please visit our website at linear.com for more information.